Okay. All right, we're going to start chapter 6. And chapter 6 talks about the structural analysis. So you're going to learn how to analyze some new structures. In particular, when we're talking about trusses, frames, and machines. And you're going to learn how to analyze those based on what you know so far in this course. We're going to use a lot of equilibrium of
You got to turn
particle.
your video off so we
Yeah.
can hear you.
Okay. So we're going to use a lot of equilibrium of particle and equilibrium of rigid bodies in this chapter. So I hope everyone had a chance to watch the lecture on truss in chapter 6, but I'm going to mention it very briefly and very quickly here. So problems like this is what we're going to deal with, which is for the load shown on the truss, use the method of joints to determine the forces in all the truss members, indicate if they're in tension or compression. All right, so truss, first we got to know what is a truss and what's a simple truss. Okay, a simple truss is usually a structure, and it's composed of slender members, means just thin members, that they're joined together at their end points, okay? So the key usually is you should be able to see triangle patterns. See that? See that there are triangles forming? That's usually indication of a truss, but not all the time. For the truss, it's important that the members are only connected at their end and not in the middle, and the loads are also applied at the pins and not in the middle. So loads are also applied only at the end, or as we call them, joints of these members. Okay, so these are important to remember. For our analysis, we always assume that members are joined by smooth pins. So every point here that members are joined together, they're all smooth pins. So there's no friction and they can rotate freely. All right. Here's a picture. Does anybody know where this picture is from?
Is that the new building that just got built on campus?
Yes, so this is just south of campus. You know, the main entrance of the campus is North Dakota State University. This is not the best picture. I was driving and, you know, holding my phone up and taking a photo for you guys. But you can certainly look at it. What you gotta pay attention is these, I don't know if you can even see it. These structures here that kind of look like this. So it kind of looks like that and forms what I'm assuming that's going to be a roof for this. So this is a truss. And based on what you're going to learn, you will learn how to analyze this, meaning how to find forces in each of these members. Okay. And that's what we're going to do. We're going to break down this structure and you're going to learn how to analyze the forces. So usually as an engineer, what you are asked is to design a structure like this. So they give you the loading on a roof, and based on the loading, which is going to be a distributed loading, you have to design and find the forces in the members. So for this class, what we usually do is we give you a structure and we ask you to find the loading in each members. Okay. So one thing that you got to know about analyzing when analyzing trusses is so before that, let me tell you something. Truss, based on what I just told you here, composed of slender members joined together at endpoints, and loads are also applied only at the end points. These three means truss has two force members. And that's something important that you remember. So you did one activity on 2 force members and 3 force members, okay? So what is a 2 force member? You all did an activity on 2 and 3 force members. So what is a 2 force member?
Member with two forces that have the same line of action and they're in opposite directions.
Okay. So a 2 force member obviously has 2 forces on it, right? But the forces have the same line of action. Okay. But they're also same magnitude and opposite direction. Okay. So for truss members, that usually means either this, right? Opposite, same line of action, same magnitude, opposite direction, line of action, or it means this. Okay. Same line of action, same magnitude, and opposite directions. So what happens in the first case, the red case, this one is what we call it a tension. It is trying to elongate the member, right? It's trying to stretch the member, that forces. And as you can see, the forces are going away from the truss, and those are in tension. On the bottom one, what is known as compression, we usually show them by C. Okay, they're trying to shorten the member. They're trying to compress it. And as you can see, they're pointing towards the member. So this is something important to remember. All of the members in a truss are 2 force members, all of them. So every member of truss is either like the red case that we have here is in tension or it's in compression. Okay, let me give you another example. So a random member. How can you make this member a 2 force member? So question is, this has been an exam problem as a bonus question. Make this member, whatever it is called, a whatever C, D, E. Make this A, C, D, E a 2 force member. How can you make this a 2 force member?
Put equal and opposite forces on to the points.
Okay, so you got to put equal and opposite forces at point A and point E. So I'm going to put an equal, like 20 newtons going this way, and opposite direction, 20 newtons that way. Opposite, equal direction.
They're not in the same line of action though.
Same line of action, that's important. This is this is not a 2 force member. Okay, so let's say I make a mistake and I put this on here. And remember, this is an equilibrium. Okay, or this is supposed to be an equilibrium. What happens here if I make this mistake and do not put them on the same line of action? What happens then?
You'll have a moment then.
A couples moment, right? Remember, 2 forces that are opposite, equal direction, and have a distance d, they're going to have a couples moment of 20 newtons multiplied by that distance d, whatever it is. Okay, so it starts rotating, so it's not going to be in equilibrium anymore. The only way that this is going to be in equilibrium and make it a two-force member is if I'm putting the forces opposite equal direction, but also they share the same line of action. 20 newtons. Okay, now this is a two-force member and it is in equilibrium because the moment of the couple is going to be 20, the distance is 0, so it's 0, so there's no moment of a couple, there's no unbalanced forces on it. Also, summation of forces in this case is going to be 0, so then it is in equilibrium. You see, so the point is it's not always going to be a straight member, same as what I have here. It can be any member as long as the forces are applied at the end and they share the same line of action. It is a two-force member and it is in equilibrium. Okay, so that's what to remember, and that's what is important for trusses. Trusses consist of only two-force members. Questions so far? Okay. So for trusses, I have two ways to analyze them. Method of joints and method of sections. Okay. So method of joints, what I have to do is draw free body diagram of what? You guys remember? It's called method of joints. That should be a good hint for you. And I have to draw a free body diagram of what?
One of the joints.
Method of joints. So I'm going to have to draw a free body diagram of each joint. Okay. In the method of sections, I have to draw free body diagram of what? Again, the name of it is method of section, so that should be a hint.
The sections in the truss.
The sections. I'll talk about what sections means, but okay. So there are only two ways to analyze trusses. Either draw free body diagram of each joint, which this problem number 1 tells you use method of joints, which we're going to go over it, or use method of sections. Okay. In method of joints, I draw a free body diagram of, for example, joint D here. It is the same procedure as drawing any other free body diagram. 3 steps. So step 1 is isolate and draw outline. I isolate joint D and draw outline of it. It's just like a little dot, little pin. Okay. Step 2 is to put active forces on there. What active forces do you see on joint D in this picture? What active force do you see on joint D in this figure that we have on the corner?
600 newtons.
I see 600 newtons going this way. If I ask you, is this in compression or tension, what would you say? This 600 newtons.
Wouldn't it be tension?
It is in compression. Every time the force is pointing to a pin or pointing to a member, it is pushing on the member, it's pressing on the member, it's trying to shorten the member, compress the member, it's in compression, okay? Every time it's going away from it, it's going to be tension. All right, step 3 is reactive forces. So when it comes to trusses, the reactive forces are going to be forces that are along the members. I see 2 forces here. I see one along member DE, and I see another one along member DC. Okay, so when you're drawing free body diagram of joints, you got to put two forces along, or sorry, not two forces, forces along the members that are connected to that pin. And here's my method all the time. Draw for both of these. Draw unknown forces in tension, meaning going away from the pin. Okay. What kind of analysis would you use for this free body diagram based on what you've learned so far?
A particle in equilibrium.
Particle. So this is an equilibrium of a particle. Chapter 3. Okay. The reason is all the forces are either going to point D or going away from point D. So they are all what we call it concurrent, means they go to the same point. So what you have is summation of forces in X equals 0, summation of forces in Y equal 0. You should have up to 2 unknowns on every joint because you only have 2 equations. Summation of forces in X, summation of forces in Y. In this case, for joint D, we have 2 unknowns, so we should be able to figure it out. Method of sections, on the other hand, is when you make a cut through your truss, and the cut goes through some members. It's an imaginary cut, okay? Then you draw free body diagram of 2 sections of the truss. If I make a cut like that, then I'm gonna have a free body diagram like this. Okay, this is my D, C, E, and this is my cut, and then I have another one like that. Okay, I'm just gonna connect these together. A, B. All right. So I just make the cut through the truss, leaves me with 2 halves, and I can draw a free body diagram of the half. Every time you make a cut, you have to put a force where the cut used to be. And again, these are all unknown forces, so we all draw them in tension. This one, let's call this one EA. This one, let's call it EB. And this one, let's call it CB. We have to do exactly opposite on the other side too. I'm going to draw this one AE or EA, doesn't really matter. The other one is going to be BE, and the other one is going to be BC. And you see how I drew all of them in tension? They're always going away. So this is what known as method of sections. You make 2 sections, draw a free body diagram, and then you start solving. There are forces here too, all right? I didn't draw those. I was focusing purely on the section, but we can do that. But there are 2 forces here too. I didn't draw them either. So what does this remind you of, this type of analysis? The first one was equilibrium of particle. What is this one?
Equilibrium of rigid bodies.
Rigid bodies, because all the forces are not going through the same point right now, right? So this is like an equilibrium of rigid body. So the equations you have is summation of forces in X equals 0, summation of forces in Y equals 0, and summation of moments about any point you want equal 0. So this, you can have up to 3 unknowns in this case, which the section I have, CB, EB, EA, there are only 3 unknowns. You should be able to solve them. So remember, Equilibrium of particle when it comes to joint, equilibrium of rigid body when it comes to a section of a truss. Okay, questions before we start doing an actual problem with numbers? Okay. And I'm going to explain when use method of joints, when use method of sections. You can absolutely use them for any truss. Doesn't have to be joints or section, worse either or. But sometimes it's better to use joints. Sometimes it's better to use sections. Sometimes the problem tells you which one to use. Okay. But in any case, you can use both of these methods for any truss to find forces on the members. All right. Let's see. Just want to make sure I have enough slides. Okay. So for loads shown under truss, use method of joints to determine the forces in all truss members. Indicate if they're tension or compression. When you're using method of joints, remember, it's like equilibrium of a particle. So you should use or start with a joint that has two unknown forces and not more. If I start at E, do you see how many members are going into the point E? Those are how many unknowns you're going to have. ED is unknown, EA is unknown, EB is unknown, EC is unknown. All right, so I have 4 unknowns. I can't do much. If I start at C, all the members that they go to point C are an unknown force, DC, CE, CB, and so on. Joint D is a pretty good one. If I start, it has 2 members going to it. So I only have 2 unknowns. I kind of drew the free body diagram already, right? Step 1, isolate, outline. Step 2, put active forces. Active forces, I have the direction of the force, so I can't change that one. The unknown forces, I told you to always draw it in tension. So F, DE or ED, really doesn't matter what you name them. And another force of FDC. This one, we have the slope triangle 4, 3, 5. I get it from here. Okay. 3, 4, 5. Okay. 2 unknowns, 2 equations. I should be able to do it. Summation of forces equal in x direction equals 0. So from this point on, it's not new. It's just review of chapter 3 now. Okay. What I see is minus FDE. What is the x component of that? Is it 3 over 5 or 4 over 5? 3 over 5. And DC is a straight down, minus 600 Newton equals 0. Okay. FDE is going to be minus 1000 Newtons. Okay. The problem says indicate if they are in tension or compression. So now FDE, is it tension or is it compression?
You had it made as tension, but it's actually compression.
It is actually compression. So all you have to do is put a C next to it. Okay. I drew it as tension because I told you, draw all the unknown forces in tension. Unknown forces. Okay. And the problem gave me a negative sign in my answer. So I know it should have been the other way. So it isn't compression. That's all you have to do. Put a C next to it. All right. So now you got to pick your next joint. Joint D is done. I got to kind of move my way down. I got to either pick C or E. Which one would you pick next? Remember, it should have only 2 unknowns.
B.
B. How many unknowns does B have?
2.
B has 4 unknowns. You're forgetting the support reactions, Bx and By from the pin. Okay, what else? What would you next pin be? Someone said anything in the chat?
C.
C, someone said C. So my next, yes, my next was also C because C has 3 members going into it, but DC is no longer, oh, I didn't find DC yet. Okay, never mind. Sorry, my question was confusing. Now I get it why. I haven't found DC yet. I still have another equation to write here. Summation of forces in Y equals 0. FDE, which is, I'm going to write it as is right now. It's going to be negative because it's pointing down. This time is 4/5. I'm only looking at my free body diagram. I haven't looked at this number yet. Okay. The other one I have is minus FDC, and that's it, equals 0. Now I'm going to replace FDE by its value. FDE is minus 1000 newtons. So I'm going to take this, put a minus 1000 newtons here. Okay. I want everyone to look at it and kind of understand these minuses. Just look at it for 10 seconds, 5 seconds. When I write my equation, I go based on what I have as my free body diagram, but then I substitute the value that I have in there. Okay. FDC is going to be 800 newtons. Okay. Now this is this in tension or compression? Tension, right? Because I drew it as tension and my answer is positive, so that means my direction was okay. All you have to do is put a T next to it. All right. So now I can ask you a question, what is the next pin, which already sets, someone said C. Because now this member force is known, this one is known. If I draw point C, I only have 2 unknown forces on there. So let's see. FBD of joint C. Step 1 is isolate and outline point C. That's it. Step 2 is put active forces on there, which I already see a 900 Newton. Okay. Next is put inactive, or sorry, reactive forces, and they're unknown. I told you draw unknowns in tension. Gonna draw an FCB here. Going to draw an FCE here. And DC is not an unknown. I already have it. And it's 800 Newton. And which way should I draw it? Pointing up or pointing down at point C?
Up.
Let's see. Okay, which way should I draw it? Someone said up. So look at point D. From point D, it's pointing down, right? But when it reaches point C, which way should I draw it?
Up.
Up, okay. Anybody saying I should draw it pointing down? So FDC is tension. Once a force is a tension, it's always tension. Okay. Meaning member DC is in tension. Okay, that's what the meaning of it is. So force DC is tension, and if I want to draw it in tension, it should go away from point C. So I have to draw it this way and not pointing down. All right. So someone might say, hey, how come point D from point D is pointing down? How come it's pointing up at point C? Here's the answer to that question. I have member DC here. This D, this is C. I'm totally disassemble it. This is my pin C. This is my pin D, right? I totally took it apart. 2 pins and a member in between. Let's see. At D, FDC is pointing 800 newtons down. There is an opposite equal force on member D that is also 800 newtons going that way. Okay. There is an opposite equal force of 800 newtons at point C because this is a 2-force member. A 2-force member has 2 forces, opposite direction, same line of action. As a result, force C has an 800 Newton going on it. Now do you see the difference? When I put this all back together, these 2 forces are going to cancel each other out. These 2 forces are going to cancel each other out. I am back to my pin D, C, D. Everything is okay now. Back to normal. I didn't put the 600 on there. I'm just drawing the D and C. So to understand. Now let's see. I'm going to make a cut in the middle. I like to disassemble it even more. Let's see what happens. I have this 800 newtons going up. This is point D, and better make a better cut. I made a cut. Okay, and here's my other side of the cut, C. What happens in the center now that I made a cut? What do you think should go in the center? Here's a hint for you. This little guy here is also a 2-force member now.
Shouldn't it be 800 pointing both directions?
So it's going to be 800 going this way, going 800 going this way. See that? By cutting it, I divided into 2 little 2-force members again. You can keep cutting. You can cut this one, same thing, and keep cutting the same thing. So every time you cut through a member, you are revealing the forces that is inside of that member. And that's how we have method of sections, and that's why we can use method of sections, because once you make that cut, the forces are going to show themselves. All right. So this is just kind of in between. I want to clarify that. All right. So this one is pretty easy. You are going to have summation of forces in x equals 0. FCE is going to be minus 900 newtons, and that makes it a compression. Okay. Summation of forces in y direction is 0, and FCB is going to be 800 newtons, and that makes it a tension. Okay. Which one would you pick next? Now, this is also known. This is also known. So if I draw joint E, I have 1, 2, 3, 4, 2 of them known, so I have only 2 unknowns. I can do it. So let's draw a free body diagram of joint E. Okay. Joint E, step 1, isolate, draw outline. Active forces, there are no active forces on it. There are no external forces on it or active forces. All I see is 4 forces that are going away. So let's see. DE, this one, let me figure it out. How much was it? DE was 1,000 newtons and it was compression. CE was 900 and it was tension. Okay, so let's draw those two. And 900 force, sorry, that was compression, wasn't it? Compression. So a 900 newtons compression, this is known. A 1,000 Newton compression. Okay. Now I get to my unknown forces, and I told you, draw unknowns in tension. I have F EA going this way, and I have F BE going this way. This little guy here is 3, 4, 5. No, it's going to be 4, 5, 3 this way. And the other guy is going to be, so it's 3, 4, 3, 4, 5. 4, 3, 5. There we go. Okay. Is that correct, Colton?
Yeah, now it is.
Yeah, okay. All right, summation of forces in x equals 0. Anything that points this way is going to be positive. So I have F EA. It's going to be 3 over 5. That's going to be negative. I have FBE. This is going to be 3 over 5. Yeah, that's going to be 3 over 5 minus 1,000. That one is also going to be 3 over 5 minus 900 newtons equals 0. Next, I have summation of forces in y equals 0. This one has two unknowns. I have FEA, and it's pointing down, so it's going to be negative. This time it's going to be 4 over 5. FBE also pointing down, so it's negative. So that's going to be also 4 over 5. And then minus 1,000. That one is going to be also 4 over 5. And that's going to be equal to 0. So I have two unknowns, two equations. I should be able to find those two. It's going to be minus 1.75 kilonewtons, and then FBE is going to be plus 750 newtons. So this one is compression, this one is tension. Check my signs and check my math. I might have somewhere down the line I've switched 3 and 4 in there. So please check the answer, but the equations should be correct. Okay. Questions? Again, pretty much nothing is new here. You know how to draw a free body diagram of particles, right, from chapter 3, and you know how to use these two equations. Again, this is totally chapter 3 theory. So theory of it is not new. It's just putting these and applying these to a truss and to member. That part of it is new. But the equations and free body diagrams, these are well covered before in chapter 3 and after that. Okay. Okay. I don't know how much time we have. I can start on a method of section 1, but forget, we'll probably finish it next time. Any questions before we go on with method of sections? Okay. So let's look at a problem like this one. For the loads shown on the truss, use method of sections to find forces in members KJ, KD, and CD. All right. So we use method of sections usually when we only are interested in forces in some of the members and not all of them. In the problem that I just did for you, for this truss, we found forces in all of these members, right? But in this problem, it's only interested in KJ, KD, and CD. If you want to use method of joints, you absolutely can, and there's nothing wrong with it. The problem is you have to start from one of the joints and kind of work your way through. You have to draw a free body diagram of every single joint to get to, for example, KJ or KD or CD. All right, so there's a lot of extra work that is not needed. So in this case, that's when we are going to use method of sections. The first thing we do in method of sections, we're going to make a cut, imaginary cut, that goes through these members. Okay, so let me see. KJ, KD, and CD. Okay, I think I figured it out. If I make an imaginary cut, you see that? It goes through all three. And I just told you, if you cut a member in half or just cut through a member, the forces are going to show up. Okay. So if I make the cut, then I'm going to have to draw a free body diagram of each section. Step 1 is outline of the section. Let me see. This is it. This is my outline of this section. A, L, K. Some people like to draw a little bit of the members too. That's totally fine. Nothing wrong with it. Okay. You do not need to draw every single member of the truss because you're just doing outline of the section. The other side, also outline of the section. Let me see. This is G, this is H, this is J. And if you like to draw a little bit of the members too, that you can. Okay. Step 2 is put active forces on there. Active forces, what I see is one is at B, 20 kilonewtons. There's one at C, 20 kilonewtons. I don't see anything else. There's one here at D, 40 kilonewtons. Okay.
The force at C is 30 kilonewtons.
30, oh yes, 30, thank you. 30 kilonewtons. Okay. Next step is to put reactive forces. We have two types of reactive forces. One is what we learned in chapter 5, which comes from the supports. Remember? I have a pin. Remember this table? Pin A. And G is a rocker or roller, whatever you want to call it. Pin A, it doesn't move in X, it doesn't move in Y, it can rotate. G, it moves in Y, moves in X, doesn't move in Y, and it can rotate. So at A, I have to put AY, AX. At G, I have to put a GY. Let me ask you this question. Why do you think, and this is very, very common in bridges, and I covered this in my lecture too. Why do we have pin on one side and roller on the other side? If this is a bridge, right? A footbridge. Why do I have roller on one side and why do I have pin on the other side?
Because the bridge will have to expand and contract.
So it's for expansion, contraction, for deformation, for ground movement, all of that. In statics, we assume these are rigid bodies. So we assume they don't move at all. They don't expand, contract. This is what we get. But in real life, we know that that's not the case, right? In real life, when you put forces on them, they're going to deform a little bit. So it's going to push point G out a little bit. In winter, it's going to contract a little bit and so on. So that's why usually one side is totally fixed. The other side has room for movement. So my support reactions are done. Last thing I got to do is what the problem asked me to find and the cuts that I made. Because I made cuts, I'm going to reveal 3 forces here, Kj, and I draw all of them going in tension, Kd, Cd. The other side, same thing, opposite direction, Kj, Kd, Cd. Okay. So now you have 2 options. You can pick free body diagram number 1 and solve it, or you can pick free body diagram number 2 and solve it. You can do it either way, right? Let's say you decide to pick free body diagram number 2 and solve it. How many unknowns do you have? On free body diagram number 2. How many unknowns do you have?
4.
4. How many equations do you have? How many equations do you have for a rigid body?
3.
3, right? If you want to pick free body diagram number 1, how many unknowns do you have there?
5.
5. Ax, Ay, and the 3 forces. Boy, the case is more severe here. I have only 3 questions. So now what? Now what I should do? There's no way you can solve 4 unknowns with 3 equations, or 5 unknown with 3 equations. So what do you do now? Have you
Should
learned
you make another section?
another section? No. Any other section you make, it's any cut that you make is going to give you 3 unknowns, right? So it's not helping. Have you learned anything in statics that can help you find some of the unknowns? Let me reword this problem for you. Forget about what it says here. Forget that you even know the word truss. It says find reactions at A and B. Or sorry, A and G. Can you do this? If I change the number here to chapter 5, can you do that based on what you learned from chapter 5?
Yes.
Yes, so chapter 5, you draw a free body diagram of your rigid body, which in this case, I'm done in 30 seconds, which in this case is your entire truss. So free body diagram of rigid body. Step 1, isolate, draw outline. There, step 1 done. Step 2, put active forces, 20, 30, 40. Step 3 is reactive forces, AY, AX, and GY. How many unknowns do you have here?
3.
3. And equations, you have 3. So now you can solve this. So for problems like this, the step 0, I don't like to call it step 1 because you go back to it if you need. You have to write your 3 equations for the entire truss. And you can even forget that it's called truss. For your rigid body, find the 3 unknowns, and then go back to your section. Then these are going to be known. I'm gonna solve this one on Wednesday, okay? But if you're curious and interested, you can go ahead and solve it, but I'll go over it on Wednesday lecture, all right? Okay. People who have questions, you can stay on. I'll be online. If you don't have a question, you're good to go. Have a good day. Sorry, I went a couple of minutes over. Okay, any questions?